Hello there, Mr. Sutton bringing you the AB Calculus 6-6 Extra Practice Number 1 solutions on motion and position. On this problem, we have the data for the acceleration of a car from 0 to 6 seconds. We have the velocity at time 0 is 11 feet, and they want us to approximate the value at time 6 for this velocity using a left Riemann sum. All right, so let's get our general setup. This is an FTC kind of setup here. We can say the velocity at time 6, v of 6, equals v of 0, which is 11, plus the integral from 0 to 6 of a of t up here. And let's see here, the integral from 0 to 6 of a of t, all of this is going to be approximately equal to the following. So if we're doing a left Riemann sum, that means we have to take the left acceleration value for each of our rectangles that we're making. So we have a base of 2 times a height of 5 in this case. And then we're going to have, let's see, base of 2 times a height of 2, base of 2 times a height of 8, and let's just see what all this adds up to. So we have 11 plus 10 is 21, plus 4 is 25, plus 16 is 41 feet per second, giving us answer choice E. For this problem, we have a particle on the x-axis with an acceleration given by this formula here. If at time 0 velocity is 5 over 2 and position is 17 over 4, we want the position at any time. So we basically want the position formula, x of t. All right, so we're going to have to do 2 rounds of diff-EQ working backwards from our acceleration formula. Let's start by taking the antiderivative of each side of this formula. So antiderivative of a of t is going to be v of t, because a is v prime. And then on the right side, antiderivative of e to the negative 2t, that's going to be e to the negative 2t divided by this tail of negative 2, so negative 1/2 that, and then plus c1 we'll call it. We're going to have a constant of integration here that we're going to need to figure out. So to figure out our c1 and kind of round out this velocity formula, we're going to plug in 5/2 for velocity and 0 for time, because they said at time 0 that's what our velocity is. So we have 5/2 equals negative 1/2 times e to the negative 2 times 0 plus c1. Well, e to all this is really just e to the 0, which is just 1. So we have negative 1/2 plus c1. Adding 1/2 to the other side gives us 3. So that's our c1 value. And our velocity formula then is negative 1/2 e to the negative 2t plus 3. All right, time to work backwards and find our position formula. So if we take the integral of both sides of this equation, on the left side we've got x of t, because that's what v prime, that's what x prime is v. And then we've got, let's see, this is going to be negative, actually positive 1 over 4 e to the negative 2t now, plus 3 t plus c2 we'll call it, another constant of integration. To find out c2, now we have to plug in 0 again for time, because that's what they gave us for our initial value, and an x of t value of 17 over 4. So we can write 17 over 4 equals, let's see, 1/4 times e to the negative 2 times 0 plus 3 times 0 plus c2. 3 times 0 is gone, but over here we just have 1/4. So if I subtract 1/4 from both sides, 17 minus 1 over 4 is 16/4, which means we have a c2 value of 4. Plugging that back in, we have all this stuff with 4 tacked on the end there, and that is going to be, let's see here, this is really like having e to the negative 2t over 4 plus 3t, and then we also have a plus 4, so that's going to be answer choice E. Just carefully select that from our choices here. On this problem, we have a particle traveling in a straight line with a constant acceleration of 3. Velocity is 10 at time 2. We want to know how far this thing travels in the interval when the velocity increases from 4 meters to 10 meters per second. So there's a lot of things we need to figure out here. Ultimately, we're looking for an integral of velocity between 2 times, but we need the velocity formula to figure out what those times are going to be. They're going to be the times whenever velocity is 4 and 10. And to even get the velocity formula, we're going to have to start with the acceleration formula. Well, the acceleration formula, we can just say a of t equals 3, because they said we had a constant acceleration of 3. So I'm going to do my little diff-EQ dance here to get my velocity formula out of this. And the good news is this is a pretty one to integrate. On the left side, we're going to have v of t. On the right side, 3t plus c. And they gave me an initial value for velocity, so that was nice of them. I know that when I plug in 2 for t, my velocity should be 10. So we can say 10 equals 3 times 2 plus c. So then c equals 4, and we have a velocity formula of 3t plus 4. All right, well now we need to figure out the times at which this velocity formula takes on a value of 4 and also 10. This takes on a value of 4 when we have a t value of 0. If we set this all equal to 4, subtract 4 and divide by 3, we end up with t equals 0 seconds for that. How about when this thing equals 10? Well, 10 minus 4 would be 6, divided by 3 is going to be 2, so that happens at 2 seconds. All right, so now we have our limits of integration that we need to plug in our integral. So we want the integral from 0 to 2 of our velocity. So this right here. Now, how do we know that there are no direction changes here? Well, our velocity, we have a constant acceleration of 3 meters per second per second. So that's telling us that our velocity is increasing, and it starts positive and ends positive on this interval. So we're guaranteed that velocity doesn't equal 0. We don't have any turning around of this particle over this time period. So it is just going to be straight up integral of velocity. So what is that now? This was a no calculator question, so we have to take the antiderivative of this velocity formula we just found. So that's going to be, let's see, 3/2 t squared plus 4t, evaluated from 0 to 2. So we have all this stuff with 2 plugged in, minus all this stuff with 0 plugged in. The good news is this second little bracket here just comes out to 0 because everything is being multiplied by 0. Over here on the left side, though, we have to do a little bit more arithmetic. So we've got 4 divided by 2 is 2 times 3 is 6. We have 6 plus 8, which comes out to 14 meters, and that ends up giving us choice B. For this problem, we have a particle moving on the x-axis with an acceleration given by 2t minus 7. Initial velocity is 6. We want to know at what time on the interval from 0 to 4 will this particle be farthest to the right. So we're trying to figure out when we have the maximum value of x of t, essentially. All right, well, to figure this out, we need to know a little bit more about the velocity and critical values and all that. So let me use a little diffie-q to figure out the velocity formula. Integrating both sides of my acceleration formula, I have v of t on the left and t squared minus 7t plus c on the right side. Let me now plug in my initial velocity value to figure out that c value. So velocity is going to be 6 at a time of 0 because they said the initial velocity, so that means at time 0. So all of this zeroes out except for the c, leaving us with c equals 6. So then we have t squared minus 7t plus 6. I'm going to set that equal to 0 now to figure out the critical values. And I can factor while I'm doing this. So this is going to be t minus 1 and t minus 6, all of that equals 0, giving us critical values of 1 and 6. So I need to see where I'm changing direction here. That's going to give me some clue as to when this thing is farthest to the right. So I actually don't need to test out the critical value 6 because it's outside the interval 0 to 4. My only critical value on this interval is going to be 1. So I've got a critical value at 1, and if I plug in something less than 1 but greater than 0, like 1/2, actually, no, wait, I take that back. I don't even need to plug in something greater than 0 because there's no critical value at 0. I can actually plug in 0 itself, and that'll tell me what velocity is doing. So at 0, this thing comes out with a negative, negative, positive here. 2 negatives is a positive. And if I plug in something bigger than 1, but less than 6, right, because things change at 6, so I'll plug in 2. That's going to give me a positive times a negative, which comes out negative. So looking at what's going on here, on the interval from 0 to 1, our velocity is positive. So that means this particle is increasing along the x-axis, moving to the right until I get to the t value 1. After 1, from 1 onwards to at least 4, I mean maybe possibly all the way to 6, our particle is moving to the left. Velocity is negative, x of t is decreasing. So if we're moving to the right until we get to 1, and then we're moving left afterwards, that means we must be farthest to the right at t equals 1. Choice B. For this problem, we're given the velocity of a particle moving on the x-axis with this v of t formula, and we're told at time 0 position is 4. We want the position at any time, x of t. So for this, I'm just going to use a little diffie-q. Integrating both sides here, I have x of t on the left, and this will be, let's see, t squared minus 4t plus c on the right side, using my reverse power rule. Now to figure out the c value, which is what I need to finish this problem, I'm going to plug in 0 for time and 4 for x. So I have 4 equals 0 plugged in for all the t values plus c. That zeroes out everything on the right except for c, leaving me with a c value of 4. Plugging that back in then, we have t squared minus 4t plus 4. And carefully selecting one of the answer choices here, let's see, we have t squared minus 4t plus 4. That's going to be c. B was pretty close, but c has that plus 4 at the end. So we're going to pick choice C. On this problem, we have a particle moving on the x-axis with a velocity given by sine of 2t. We're given the position at time pi over 2 to be 4. We want the position at time 0. All right, well, this is an FTC kind of problem. Our position at 0, so x of 0, is going to be x of pi over 2, which is 4, plus the integral from pi over 2 to 0 of our velocity, which is really just x prime in disguise here. All right, so let's go ahead now and take the antiderivative of velocity, because this is a no calculator problem, so we need to do it the old-fashioned way. Antiderivative of sine in general is negative cosine, but we're dividing by a tail of 2, so negative 1/2 cosine of 2t from 0, or from pi over 2 to 0. And I'm going to pull that negative 1/2 outside my little evaluation box here. So now I've got, let's see here, 4 minus 1/2 times. Now inside here, I'm going to have cosine of 2 times 0 minus cosine of 2 times pi over 2. And cosine of, let's see, 2 times 0, this is just cosine of 0, which is 1. Cosine, this is cosine of pi over here, which is negative 1, but it's being negated. So we have 1 plus 1 inside here. And then, let's see, we're doing 4 minus half of 2. That's really just 4 minus 1, which comes out to 3. So choice C. For this problem, we have Ruth riding her bike on a straight trail, and she records her velocity, which she somehow records as she's going, in this table here. Very convenient of Ruth to do that for us. So for the first part of this problem, we want to use the data here to approximate Ruth's acceleration at time 1.4. So we're basically trying to approximate v prime of t at 1.4, and we don't have the exact velocity, we don't have the exact acceleration, we don't have really anything we need except some values of velocity at various times here. So to approximate this, we're going to find the average rate of change of velocity over an interval that has 1.4 in it. That'll approximate our acceleration. Probably the best interval is this interval from 1.2 to 1.6. It's the smallest interval with 1.4 in it. So we're going to do, let's see here, v of 1.6 minus v of 1.2 all over 1.6 minus 1.2. And I'm going to write that the acceleration at 1.4 is approximately equal to this. Not equals, it's not exactly this. So plugging in the actual numbers from the table, this is really 16.3 minus 17.2 over the denominator we had before. And you could actually just stick units on the ends of this, which since its acceleration is going to be miles per hour squared, and call it a day. Or you could actually calculate this out. I would recommend you use a calculator because this was a calculator problem. So let me do that now. So here I go, entering this into fancy fraction mode. And that comes out to negative 2.25. And again, that's going to be in miles per hour squared. For this next part of the problem, using correct units, we want to interpret the meaning of integral from 0 to 2.4 of v of t dt in the context of the problem, and then approximate it using a midpoint Riemann sum with 3 intervals. All right, so let's do the whole meaning piece of this first. If I'm integrating velocity, I'm getting the total change in position of Ruth over the interval from 0 to 2.4. So this is going to be change in position, and they want the units. So since we're going miles per hour for velocity, integrating that just takes off a time unit and gives us miles. So this is in miles. And again, we need to specify the interval here to get credit on this. So this is going to be the interval from 0 to 2.4 hours. This gets you full credit. Anything less, not so much. Now we want to approximate this value with a midpoint Riemann sum. And I'm using 3 subintervals, and this is going from 0 to 2.4. So we're going to use the whole table here. Our first interval is going to have to be between 0 and 0.8. So I have a base of 0.8, and we're going to use the midpoint output value of that, 11.8, as our height for this rectangle. So we have approximately equals 0.8 times 11.8 plus base of 0.8 times a height of 17.2. Again, we're using the middle value, plus 0.8 times 16.8. And you have to put units on the end of this, so this is going to be miles. You could be done if you did that, or you could figure out on your calculator what it all comes out to. So if you do feel compelled to see what this number actually becomes, and you want to save a little bit of time, you could factor this 0.8 out of all of this stuff. It's a common factor, and then just add everything inside of parentheses, giving us 36.64 miles. For this part of the problem, for 0 to 2.4 hours, Ruth's velocity can be modeled by the function g, given by this crazy function here. According to this model, what was her average velocity during that time period? So for average velocity, we need 1 over the interval length, so 1 over 2.4 minus 0 in this case, times the integral over this period, so integral from 0 to 2.4, of whatever it is you're trying to average. We're averaging the velocity, so we're just going to put in this g of t formula, so g of t dt. No need to rewrite it here because they already told us what it was. But now we have to do this on the calculator. To make my life a little bit easier, I'm going to enter this formula in my y equals under y1, and then quitting out of here, I've got fancy fraction 1 over, and this is going to be 2.4. I don't need to write 2.4 minus 0, times, let's see, math 9, integral from 0 to 2.4 of what I just entered in y1. So alpha trace y1, there we go, dx. And we come up with an answer of about 14.064, and that's going to be in miles per hour because this is still velocity, just average velocity. On this problem, according to our model from part C, so that was using our g function that we entered in our calculator, is Ruth speeding up or slowing down at time 1.3? And give a reason. So if you want to figure this out, we just need to compare the signs of velocity and acceleration at time 1.3. And we have to do all of that on the calculator because we're using that weird g function that they use to model things in part C. So let's first find g of 1.3. That's our velocity. I can do that on my calculator by doing, let's see, alpha trace y1 of 1.3, which I already have this function entered in my y equals, so there's no need to do everything out again. That comes out to about 18.096. The important part of this is that that's a positive number. Now we need the acceleration, which is going to be g prime at time 1.3. Going to my calculator, let me do, let's see, math 8 to get my derivative. So we'll do dx alpha trace y1, and this is at time 1.3 now that we want this derivative. That comes out to 3.761. And a note that I didn't have to actually figure out formulaically what g prime looks like. Since I'm taking the derivative at a single spot, I'm allowed to do that without showing the formula to the AP graders here. So this number now, this comes out to a positive. Since velocity and acceleration, g and g prime, have the same sign, both positive in this case, that means that Ruth is speeding up at 1.3 hours.